Hello everyone. So remember that some time ago we had a lot of rules for how to evaluate limits and lots of tips and tricks. And some limits were easy because we could just use the limit laws and plug in, while other ones were harder. And the ones that were harder tended to be things that looked like 0 over 0 or infinity over infinity. And the tricks we had at that time was to try to rewrite them in a different way, try to cancel some factors, try to rationalize something like that. But those tricks were very dependent on the specific form of what we were dealing with, and they don't work for a lot of cases. So in this video, we're going to talk about L'Hopital's rule, which is a really useful rule that uses differentiation to help us find these tricky limits. So let's get started. And basically, there are a couple of different types of forms we're going to be interested in. So the first one, ones that look like 0 over 0 or infinity over infinity. So if we have a limit of f divided by g, where the top and the bottom both go to 0, this is called an indeterminate form of type 0 over 0. And if the top and bottom both go to infinity, then it's called an indeterminate form of type infinity over infinity. So if we want to try to calculate this limit, then depending on what's happening with f and g, they're kind of in a tug of war with each other. The limit could be infinity, it could be a finite number, it could be 0, it could be minus infinity, or it just might not exist at all. It could oscillate. So anything could happen. So we need some kind of rule to figure out what's going to happen. We can't just say, there's no way to say 0 over 0 equals something. There's just nothing we can do. So it's going to depend on the function. So how can we handle this? Okay, so the kind of L'Hopital's rule is a result that we're going to use in many, many different types of cases, but the result that we're using is always the same. So suppose we have two functions, which are going to be the top and bottom. So our two functions are differentiable, and the derivative of g is non-zero on an open interval containing the point we're interested in. So this is kind of a technical assumption. And then there is a really important condition that either the limit of f and the limit of g are both 0, or the limit of f and the limit of g are both plus or minus infinity. So either the top and bottom both go to 0, or the top and bottom both go to infinity. Then if this is true, we can calculate the limit of f over g as the limit of f prime divided by g prime instead. Okay, so two things to notice: that this is a rule for telling us how to find limits when the limit of the top and the limit of the bottom are both 0, or when the limit of the top and bottom are both infinity. And here we're looking at, on the right side, there is this different limit that's hopefully easier to calculate than the original one we started with. So it hopefully gives us an easier problem. And we're looking at the limit of f prime over g prime. So notice that we do not differentiate f divided by g using the quotient rule. So it's not just differentiating f over g, it's differentiating f and g separately. So that's very important. Okay, so and it's also valid for different types of limits. So here I wrote x tends to a plus, a minus infinity, but it also works for all of these instead. Okay, so bottom line, if the top and bottom are both going to 0, the top and bottom are both going to infinity or minus infinity, then we can work out the limit instead by looking at the limit of derivatives, where we differentiate separately. So here is a simple example. Let's try to find the limit of e to the 2t minus 1 over sine t as t goes to 0. Okay, if we look at what happens to the top and the bottom separately, e to the 2t goes to e to the 0, which is 1. So the top is going to go to 1 minus 1, which is 0. And the bottom sine t, sine is continuous, so we can just plug in to find the limit. That's going to go to sine of 0, which is 0. So this is an indeterminate limit of type 0 over 0. So let's go ahead and use L'Hopital's rule. So we want to differentiate the top and differentiate the bottom separately. We get 2e to the 2t, and we get cosine of t. Okay, and then we calculate the limit of the derivative of the top over the derivative of the bottom. So we look at this new quotient, 2e to the 2t divided by cosine t. So here this is the limit where we just differentiate the top and bottom separately. And hopefully this one is easier than the one we started with. And actually it is, because if we think about what happens to the top, okay, the top is going to go to 2e to the 0, which is 2. And the bottom now goes to cosine of 0, which is 1. So we no longer have the bottom being 0. Okay, so we get 2 divided by 1, we get 2. Okay, so now this limit is 2, because L'Hopital's rule tells us that that's equal to the original limit. Okay, so the limit we're trying to find is equal to 2. And just a word of warning that we have to check the conditions for L'Hopital's rule, particularly the thing we said about it being 0 over 0 or infinity over infinity. Because if we don't check them, then things could go terribly wrong and we will get the wrong answer. So for instance, suppose we're looking at this limit, sine x divided by 1 plus cosine x as x goes to 0 from the right. Okay, well, the top is going to go to sine of 0, which is 0. The bottom goes to 1 plus cosine of 0, which is 2. So the top is going to 0, the bottom goes to 2. This limit is 0. So it's not a case where we can apply L'Hopital's rule. So L'Hopital's rule is not allowed, and we don't need L'Hopital's rule, right? Because it's a simple limit we can just calculate, we can just plug in. But let's suppose that we naively go ahead and plug in and we do L'Hopital's rule. Then we would look at the derivative of the top, which is cosine, derivative of the bottom, which is minus sine x, still as x goes to 0 from the right. And then if we look at what happens, the top looks like 1. And if x is a very small positive number, sine x is a very small positive number. And then we flip the sign. This is going to be a very small negative number. So we're going to have 1 divided by a very small negative number. It's going to go to minus infinity. Okay, so of course these are not equal. So we cannot use L'Hopital's rule, and using L'Hopital's rule will give us the wrong answer. So please be very careful. Check that it's of the right form, 0 over 0 or infinity over infinity, before you just go ahead and use L'Hopital's rule. Okay, so sometimes the next comment is that sometimes we need to use L'Hopital's rule more than once. So if we differentiate once, we might get to a limit that's simpler, but it's not one we can differentiate yet. So then the strategy is to use L'Hopital's rule again to work out that limit. So for instance, suppose we start with the limit of e to the x over x squared. Okay, if we look at it, then the top, as x goes to infinity, the top is going to infinity, the bottom is going to infinity. So it's a prime candidate for L'Hopital's rule. So we jump in and we differentiate top and bottom separately. We get e to the x over 2x. And still the top is going to infinity and the bottom is going to infinity. So if we want to evaluate that limit, we can try to use L'Hopital's rule on that limit itself. So as we said, it's of type infinity over infinity. So we differentiate top and bottom separately. So if we do that, now we get e to the x divided by 2. And now life is good because as x goes to infinity, e to the x, the top is going to infinity and the bottom is going to 2 because it's just constant 2. So this limit we see is just infinity. So now we can go back a step. If this final limit is infinity, then the previous one by L'Hopital's rule must be infinity. And then if this limit is infinity, then the previous one by L'Hopital's rule must be infinity. So the limit we started with, going back step by step, the limit we started with is equal to infinity. Okay, so good times. This one we had to just differentiate twice. Okay, so now a couple more indeterminate forms we're going to be interested in are products and differences and powers. And basically with all of them, the strategy is going to be to rewrite it in a different form where we can do what we just did with L'Hopital's rule. So suppose we have a limit f times g where one is going to 0 and the other is going to infinity. Then that's kind of tricky. It depends on how fast one is going to 0, how fast the other is going to infinity. These are indeterminate forms of type 0 times infinity. So all the limits we're picking out here are the ones that look to be tricky, the ones you can't just do naively. Okay, and so to evaluate these, we're going to write the product fg as f divided by 1 over g or g divided by 1 over f. So you'll see if you multiply top and bottom here by g or top and bottom by f, both of these are equivalent to fg. So it doesn't matter which you use. And then this will convert the limit we started with to a form of type 0 over 0 or infinity over infinity. So we rewrite in this new format, and then we can use L'Hopital's rule of this new format. And because they're equal, the two limits, the limit we get is going to be equal to the limit we started with. Okay, so let's do an example like this. So we're looking at x to the 3 over 2 times sine of 1 over x. Okay, if we look at what happens to the two terms as x goes to infinity, x to the 3 over 2 goes to infinity. The inside of the sine 1 over x, as x goes to infinity, 1 over x goes to 0. So sine of that is going to go to sine of 0, which is 0. So we have something that looks like infinity times 0. So this is an indeterminate form. So we have to rewrite it as a quotient so that we can hopefully use L'Hopital's rule. And we should stick one of the factors on the bottom. And because sine is already complicated enough, I don't want to put that on the bottom because then we have to do 1 over sine of 1 over x, which is going to be a pain. So let's move the x to the 3 over 2 to the bottom. And if on the bottom we have 1 over x to the 3 over 2, we can rewrite the bottom as x to the minus 3 over 2. Right, x to the minus 3 over 2 is the same as 1 over x to the 3 over 2. And now if we look at the limit as x goes to infinity, the sine of 1 over x is still going to 0. But now x to the minus 3 over 2 is going to 0. So this is a form of type 0 over 0. And now we can just use L'Hopital's rule as we said before. So we differentiate the top and we differentiate the bottom. Okay, we have to do the chain rule for sine of 1 over x. So the outside is sine. The inside is 1 over x, so we do the derivative of the outside. So sine of u goes to cosine of u, evaluated the inside, which is 1 over x, multiplied by the derivative of the inside. So the derivative of x to the minus 1 is minus x to the minus 2. And then on the bottom, we just differentiate with the power rule. And then you can trust me, I promise that if you clean this up, you will get 2 over 3 x to the 1/2 cosine of 1 over x. So we just differentiated top and bottom. And now we hopefully look at this with fresh eyes and see if anything got simpler. So as x is going to infinity, the 2 over 3 is fixed. Here we have square root x, which is still going to infinity. And then cosine of 1 over x, as x goes to infinity, the inside is going to 0. So cosine of 1 over x goes to cosine of 0, which is 1. So we have 2 over 3, something going to infinity, something going to 1. This is going to go to infinity. Okay, so this limit is infinity. Okay, so by L'Hopital's rule, our original limit must have been infinity. Okay, so we can handle these products there are many different types of possible examples, but if you have indeterminate products, put one of the terms on the bottom. Remember, you have to do 1 over. So here, putting x to the 3 over 2 on the bottom, it became 1 over x to the 3 over 2, which is x to the minus 3 over 2. So put one of them on the bottom with this trick, and then switch it to a question and do what we did before. Okay, so next up is differences, which is a little bit less elegant. So suppose that we have two things going to infinity, and we want to work out the limit of the difference. So the limit of f minus g, where f and g both go to infinity. This one, it depends on what exactly the thing we have looks like, but basically the strategy is to try to factor something or find a common denominator, or maybe rationalize to write it as a quotient, which is an indeterminate form. Okay, so here is an example. So as I said, we either find a common denominator, rationalize, or factor, or just do something to rewrite it as a quotient. So here we have the limit as x goes to 0 from the right of 1 over x minus 1 over e to the x minus 1. And if we look at what's happening, as x goes to 0 from the right, 1 over x goes to infinity. And e to the x goes to 1 from the right. So this is going to go to 0 from the bottom, and from above rather. And when we flip, we get infinity. So both of these terms are going to infinity. So we have infinity minus infinity. We have to do something. Let's find a common denominator since we have fractions. That's the only thing we can do. And our common denominator is going to be x times e to the x minus 1. Okay, so if I want to write it with a common denominator as x times e to the x minus 1, the top term we're going to have to multiply top and bottom by e to the x minus 1. The second term we're going to have to multiply top and bottom by x. So our new numerator is going to be e to the x minus 1 minus x. Okay, and now we can check as x goes to 0, the bottom clearly is going to 0, and the top is also going to 0. So this is now of type 0 over 0, so we can use L'Hopital's rule and do whatever we did before for the quotients, which was the case we started with. So we differentiate top and bottom, and okay, if you use the product rule, then and you take k, you'll get this. And then we check again what happens. So as x goes to 0, the top is going to 0, and the bottom is going to, again, 0. So it's still of type 0 over 0. Let's differentiate again and see if we get anywhere better. Okay, if we differentiate again, we get, for differentiating the top, we get e to the x, and if we differentiate the bottom, we get e to the x plus x times e to the x plus e to the x, where here the two terms come from differentiating x e to the x with the product rule. So we have e to the x divided by 2 e to the x plus x e to the x. And now the good news is that on the top and the bottom, there are always e to the x in every factor. So we can divide through by e to the x to write it in this simpler form, 1 over 2 plus x. And now this is much easier to find the limit of, right? As x goes to 0, this goes to a half, right? The bottom is going to 2, the top is 1, this goes to a half. Okay, so if this final limit is a half, then by L'Hopital's rule, the previous limit must have been a half. And then by L'Hopital's rule, the initial limit we had must have been a half. Okay, so the limit is a half. Isn't this fun? Okay, and then finally, the final case is indeterminate powers, which are when we have limits that look like f to the power g that are of the form 0 to the 0, infinity to the 0, 1 to the infinity, which are tricky ones to deal with. So the strategy is to write it as y equals f of x to the power g of x, and then take natural logs of both sides. So we write this indeterminate power we're trying to deal with as y. We take logs of both sides. So ln of f of x to the g of x. Remember that powers we can bring out of the logarithm. So we get g of x times natural logarithm of f of x. And now this is a product, and it becomes an indeterminate product. So now we can use whatever we just did for products and quotients to evaluate this limit. And then we have to be careful that this limit is ln of y, whereas we started with y. So if we evaluate this limit instead, at the end, we're going to have to take the exponential of whatever we get to find the limit we started with. Okay, so as I said, here we find the limit of this new thing. Suppose it's called L. Then afterwards, we want to go back to the original thing we started with, so we have to do exponential of both sides. So our limit of y is going to be e to the L. Okay, so bottom line, if we have an indeterminate power, write it as y, take natural logs of both sides, simplify. That brings you to a product. Do whatever we did before to find that limit. That's going to give you the limit of the logarithm of what we started with. Then you want to do e to the power of it to find the limit we started with. Okay, so here is an example like that. So find the limit as x goes to infinity of x to the power of e to the minus x. So as x goes to infinity, the base, which is x, is going to infinity, and the power, which is e to the minus x, is going to 0. So it looks like infinity to the power of 0. So it's an indeterminate power. So let's start by writing y equals x to the power of e to the minus x, which is what we said to do, and take natural logs of both sides. ln of y is ln of x e to the minus x. We bring out the power, we get e to the minus x times natural logarithm of x. So here is our indeterminate product. And then we were supposed to find some way to write that as a quotient so that we can use L'Hopital's rule. And then here we're very lucky because already the e to the minus x is 1 over e to the x. So we can very easily write it as a quotient. Sorry, here should be ln x divided by e to the x. Okay, my mistake here. Ln x divided by e to the x. Okay, which is of type infinity over infinity, so we have to differentiate top and bottom. We are going to get 1 over x, and then, sorry, rather than having e to the x, here again it should be e to the x. So we get 1 over x divided by e to the x. And then the limit of the top is going to be 0, and the limit of the bottom is going to be infinity. Right, so here on the top we have 1 over x. Here was supposed to be e to the x. We differentiate, we get e to the x. So the bottom is e to the x, which is going to infinity. The top is going to 0. So we have 0 divided by infinity. This limit is going to be 0. Okay, so what was that? That was the limit of ln y. Right, so here the limit of ln y we said is going to 0. And now if we want to find the limit of y itself, we have to do exponential at both sides. So if we take exponentials, we're going to get the limit of y is e to the power of 0, which is 1. Okay, so the limit of the thing we started with, we have to take exponentials of this number that we got. This is going to be 1. Okay, so that's everything for here. Sorry with the confusion here. So just to say one more time, e to the minus x ln x becomes ln x divided by e to the x. Then we differentiate, we get 1 over x divided by e to the x. The top is going to 0, the bottom is going to infinity. This limit is still 0, as we said. Okay, so the limit of ln y is 0, but that's not the limit we started with because we started by taking natural logarithms. So to get the limit we started with, we have to do e to the power of that. So e to the power of 0, which is 1. Okay, so just to remember what we did, we started off with L'Hopital's rule. We said if it's 0 over 0 or infinity over infinity, we differentiate top and bottom, and hopefully we get a simpler limit that's equal. Sometimes we have to do that more than once, maybe twice or however many times. And then there are products that we can rewrite as quotients. Differences we try to rewrite as quotients. If we have powers, then the strategy is to write y as whatever power we're trying to find, take natural logs of both sides, and use whatever we did before to find that limit. And at the very end of that, we have to do exponentials of both sides. Okay, thanks everyone. See you next time.